Hello, everyone. The following is the third in a series of lectures covering Chapter 39. Today, we will be talking about the Lorentz coordinate transformation equations, as well as the Lorentz velocity transformation. As we've seen in classical physics, every frame, and for the purposes of special relativity, we're just going to be talking about inertial frames. They all have their own coordinate system. As a simple example, we'll have two observers, O and O prime. One can be seen as standing still. The other is skating away with some horizontal speed off to the right. So due to the relative motion, they must be in different frames. Let's call them S and S prime respectively. Now, suppose that you now see two events happen. Let's call them events P and Q. Both observers can see the events occur, and because they're in different frames, there might be some small disagreements. For example, since observer in S prime frame is moving, if the events are happening on the right side, he'll probably witness them a lot closer to where he is than observer O, who's farther away from the events. However, they both would agree that wherever the events occur, the distance between them, so say the two events are just, maybe two fireworks going off or just two cars honking their horns, they will agree that the distance between the cars or the fireworks are the same in either frame. And they will also agree in classical physics that these events are happening simultaneously. But as we learned, once a frame moves at near relativistic speeds, the distance between 2 points in space, this will apply to the distance between these two events, and whether or not they're simultaneous, can change as frames begin to move near to the speed of light. So classical physics coordinate transformations do not account for length contraction and for lack of simultaneity at relativistic speeds. So we need to change how we deal with coordinate transformations to make them compatible with special relativity. So Galilean equations for the coordinates of anything in the moving frame S prime are pretty straightforward. In this case, we're just saying that S prime is simply moving to the right, so only the x coordinates different from the y and z coordinates of the frame S. So you can kind of see in the bottom right here that the observer O prime, moving to the right is closer to the two events. But either way, in classical physics, they agree that the distance between them should be the same. However, to make them compatible with relativity and the notions of length contraction and time and simultaneity, the actual coordinate transformations include a gamma factor. So to switch from the frame S to S prime, you need to account for the Lorentz factor gamma, though only for those coordinates that are associated with the direction of your velocity. So in this example, the observer in frame S prime, the frame is really just moving to the right. So this only really has an effect still on the horizontal coordinate x to x prime, not as a factor of gamma. But since there's no speed component in the y or z direction, those coordinates remain the same. But also note that the measurement of time is also different. The time and position, at least horizontal in this case, in the S prime frame depend on both the time of position of events as seen in the S frame. So you can't consider space and time separately when you do these coordinate transformations. You have to account for both. And if you have coordinates in the S prime frame, you can also go back to the S frame as well. You just rearrange the transformation formulas to your need. So with these proper coordinate transformation equations, you can also see how length and time intervals would change when measured from frame S to S prime. So you can see then that length intervals measured in the S prime frame not only depend on the length interval measured in the S prime, but as well as, again, the time that passes. The same thing for time intervals in the T prime, in the S prime frame as well. So this factor here, will account for the effect of length contraction, and this factor here will account for simultaneity. Basically, unless two events happen in the same location, they will not be simultaneous in both frames. And still, because the speed's only horizontal, then distances in the y and z direction don't change, so the distance intervals there won't change either. So in this example, just kind of showing you how simultaneity is built into the Lorentz transformations. In this case, they're saying that in the boosted frame S prime, they're seeing two events happen at the same time with some space interval, some distance between the events, delta x prime. And despite the fact that in the S prime frame, they happen simultaneously, because there's some distance between them, you'll see that in the S frame, not prime, S frame, the time difference between the two events depends on the distance between the events. And again, if the events were happening at the same location, then delta x prime will be 0, and you'd see them occur simultaneously in the S frame. But in this case, because the events are happening some distance apart, they will not be simultaneous in the S frame. This is what we saw in the example where Bob and Alice were seeing two lightning bolts, and the there's a train right between them where Bob is and Alice is on the ground. So Alice, in this case, she's seeing the lightning bolts hit at the same time, but there's some distance between them. So for Bob, who's moving relativistically, the fact that there's a distance between them means that he'll actually see one bolt striking first and then the other, though they were simultaneous for Alice. And also, the transformation formulas being relativity compatible also account for time dilation. So if you're considering a frame where you can keep proper time, that means that you're looking at a clock and you're at rest with the clock. So the clock's position never changes. So basically, you're saying that you're in frame S prime and you're at rest with respect to a clock. So you're keeping time interval in the clock, close ticking the clock some time interval little t prime. And in your frame, you're moving the clock so that the position of the clock never changes. This whole term is 0. So when you jump to the frame S to get the time interval here, little t, you'll see that the time interval measured in frame S, where the clock is moving, is now a factor of gamma times the delta t prime, which is in this case proper time. And this would be the effect of time dilation occurring, since in frame S, you are not keeping proper time, you're not moving, you're not at rest with the clocks, the clock's moving relative to you, so you would see the clock slow down. Okay. Recall how being able to transform coordinates also allows us to measure speeds and velocities relative to whatever frame of reference we are in. So it was simple enough to transform velocities to any other inertial frame in classical physics. So let's go back to the example we talked about earlier. If we have some object with some velocity vector, doesn't really matter what the velocity is, just that in the real world it can have an x, y, z component, and we still have the same observers as before, O and O prime in S and S prime frames, and O observes the ball having this particular speed. And the question is, well, what's the speed relative to the observer here in frame S prime? So we can't use the classical formula for relative speeds anymore. We need to make it Lorentz friendly. We need to make it relativity friendly. So we now have a new way to transform speeds to a relativistic frame of reference, which now at the top of the formula, we actually just have the classical formula for finding out what the relative speed is in a moving frame. But now there's this extra term here in the denominator that again accounts for keeping the laws of relativity in check. So because in this example, the S prime frame, the observer there on a little skateboard is moving to the right, still speeds measured have to comply with relativity. So the total speed of this object, no matter what frame it's being seen in, right, has to be obviously no higher than the speed of light, right? The speed of light is still invariant, so whichever frame, of course, is measuring the speed of light, they'll both get the same measurement. So this results that the all coordinates for an object speed actually change in a moving frame. So despite the fact that the frame S prime is only moving in the x direction, the y and z components of the object speed also change in the S prime frame. They're not constant like the y and z prime were before. So you'll note that you'll have the transformations here to go from the speed of the object in frame S to S prime, and the formulas look similar enough, just that for the horizontal component, right, there's a term to account for the fact that the frame is moving in the x direction. The y and z components, the numerators are just the speeds of those directions as seen in the original frame, but now you're dividing by this extra term that accounts for relativistic effects. And also, if you want, you can always rearrange the formula so you can jump back from the prime frame to the original frame. The Lorentz transformation equations, again, are a more accurate description of space and time since they comply with the rules of relativity. However, when you are dealing with speeds that are much less than the speed of light, we call this non-relativistic situations, non-relativistic frames, then you can approximate the velocity transformations and just the coordinate transformations back to the classical ones. So if you go back to your velocity transformations here, but frame S prime is moving, with a speed much less than speed of light, and then roughly the denominator in all of these just kind of goes back to 1, and you end up with the classical formulas again. So it's not really something we worry about in everyday life, in everyday physics. And just to show why the Lorentz transformation formulas are what they are, they're there to account for the fact that, again, one of Einstein's postulates, one of the two, is that the speed of light is constant in all frames. So if the thing you're measuring in frame S is a ray of light, so its speed is actually that uh, of light, and in this case, just moving one direction to the right, then when you transform that speed as seen by frame S prime, that speed, of course, is still c moving to the right since it needs to be constant. So quick quiz here. You're driving on a freeway in your relativistic car, so it's pretty fast. and a technician's in front of you. He shoots a searchlight up into the sky, and the question is, what's the vertical component of the searchlight's velocity? So somebody's shooting a light straight up, and you're moving towards the headlight there, the searchlight. And from your point of view, the light is shooting up, but it's also moving towards you. So you see that there's two components to the light's speed. There's a component that's shooting into the sky, and that's a vertical component, but there's a horizontal component that's moving towards you. But this is light, so the total speed should be equal to c. Since it has two components, each independent component then must be less than c, so that together, when you combine the components, you get a total measurement of c. So again, it's okay for the magnitude of a single component to be less than c, as long as the total magnitude of the beam of light is still equal to c. Okay, so this is the second question in the quick quiz. It's a different take. Now you're still driving on the freeway in your super fast car, but now the technician points a searchlight right at you. So it's just a horizontal searchlight. So from your frame of reference, the light just coming towards you, and there's only a horizontal component. So because there's no vertical component at all, it's all horizontal, then the magnitude itself, horizontal, which means that by the laws of relativity, that component must be equal to c. Anyways, that's all for the Lorentz transformation equations. I hope you join me